Okay, let's draw the single line diagram of the voltage source rectifier. And it is basically done to find out what should be the modulating voltage. So that single line diagram is like this. You have the source, you have the line impedance, here the resistance is also considered, and here you have the modulating voltage V mod. And let's see, in time domain, this is the source voltage, this is the modulating voltage which is required to be produced through that rectifier. You have the source inductance and the source resistance, and the instantaneous current is IST. We are taking the instantaneous values because we have to calculate V modulating signal instantaneous value, so that it can be implemented in the rectifier. If you write down the equation of this, then the source voltage is equal to RS IS plus LS DIS upon dt plus V mod. Let us say we are considering A phase, and therefore this source voltage is V max Vm sine of omega t, and we want the current in this particular phase to be, let us say, I max sine of omega t plus phi. So the current is displaced from the voltage by an angle phi. It may be leading, it may be lagging, depending upon the value of phi, plus or minus. This is for one particular phase. Similarly, for the other two phases, you have Vm sine of omega t minus 2 pi by 3. This also minus 2 pi by 3. And for the third phase also, sine omega t plus 2 pi by 3, and current also plus 2 pi by 3. Let us put Vs and Is in this equation. Before that, V modulating signal is basically given by Vs minus Rs Is minus Ls d by dt of Is. We have to find out the modulating signal, that's why we have written it like this. Substitute V and I in this expression. So it is Vm sine of omega t minus Rs I max sine of omega t plus phi minus Ls d by dt of I max sine of omega t plus phi. Just expand it. This becomes Rs I max sine omega t cos phi plus cos omega t sine phi. The second term is minus Ls. If the product of two, I max is not constant. Depending upon the load requirement, I max may keep on changing. So we have two terms. One is simply sine of omega t plus phi di max upon dt. This is one term. And second is minus ls I max d by dt of sine omega t plus phi. This becomes Vm sine of omega t as it is minus Rs I max sine omega t cos of phi minus Rs I max cos omega t sine of phi. Second term. Here you have Ls sine omega t cos phi di max upon dt. Just expand it. Minus Ls cos omega t sine of phi di max upon dt. Third term, it is minus Ls. If you take the derivative of this, it is omega times cos omega t plus phi. Omega comes here. Then you have I max cos omega t plus phi. Expand it. Cos omega t cos of phi, one term, minus sine omega t sine of phi. Combine cos omega t and sine omega t terms together. So first sine omega t terms, it is V max, then you have minus Rs I max cos of phi, this term, then you have minus Ls cos of phi di max upon dt, third term. And here you have the fourth term, minus minus plus omega Ls I max sine of phi times sine of omega t. Now cos omega t terms, this is minus this thing. This is minus this thing. This is also minus this thing. So let's take minus common. Then you have Rs I max sine of phi. Then here you have Ls sine of phi di max upon dt, and third is this one. It is minus is taken outside, omega Ls I max cos of phi cos omega t. This is what V mod is in general. If let us say you want unity power factor, for unity power factor operation, phi is 0. Put it in this one. So V mod is equal to, it is Vm minus Rs I max cos phi 1. It becomes minus Ls d I max upon dt. This will become 0, sine of phi. So this is sine of omega t minus, this term is 0, sine of phi. This is 0, sine of phi. Only this term is left out. Omega Ls I max cos phi is 1, sine of omega t. So for unity power factor operation, this is the equation. And if you want to implement this particular equation, you can see this one. For one particular phase it is shown. The source voltage is sensed of that particular phase. Vm sin omega t and cos omega t. These three terms are obtained from that particular phase voltage. The reference voltage is compared with the actual output voltage. Error is processed in a controller to generate the max current I max, similar to the previous instantaneous current control. Now this I max, now there are three terms in this modulating signal. One is Vm sin omega t, which comes directly from the source. Then you have minus R I max sin of omega t. Then you have minus SLX, basically indicates derivative of I max. So it is minus Ls di max upon dt times sin omega t. And then in cos omega t you have simply I max minus omega Ls cos omega t. All the three terms are added to generate the modulating signal for phase A. Like that, for modulating signal for phase B and the modulating signal for phase C are generated. While doing this entire exercise, we assume that the source, this resistance R and the inductance Rs and the inductance, they are known and they are fixed. If they keep on changing or they are not properly known, your modulating signal will not be properly calculated. So we can generate instantaneous values of three modulating signals, and once you have the modulating signals, you can use sinusoidal PWM technique. Just compare the modulating signal with this carrier wave, and that carrier wave intersection will generate the pulses for the upper and the lower devices, and in that way you are generating the modulating signal here as the reference one. And if you have generated the modulating signal properly, you can control the current through this particular phase. Now, if you assume that the circuit is in steady state, if you consider this to be under steady state, I max is constant and therefore di max upon dt will be 0. In that particular case, if you write down the equation of this single line diagram, instead of instantaneous voltage and the current, you can use the phasor notations. You can represent it in terms of phasor. So your source voltage is equal to the modulating voltage plus Rs times Is plus Js Ls times Is. And using this equation, you can find out what is the modulating signal. It is Vs minus Rs Is minus J. It can be written as Xs Is. Let it keep it to omega Ls because in the phasor diagram we have this. You can see that V or Vs is basically V modulating plus Ris plus J omega Ls Is. So if the current is required to be in phase with the voltage, then the modulating signal should occupy this position, which is lagging voltage by an angle delta. If you reduce this angle delta, the phasor diagram remains the same, but the current magnitude has come down. If the delta has become 0 and the modulating signal and V are same in magnitude, then the current is 0 like this. If the modulating signal exceeds this particular voltage by an angle delta, current becomes opposite. Now power flow is in the reverse direction. That is clear from here also. If that angle increases, there will be more regeneration taking place. So just by controlling this V modulating signal, one can control what will be the net current. Another thing which you can observe in this particular control strategy is that only the source voltage is sensed, the source current is not sensed. So there is an advantage of removing the current sensor. You only have to sense the source voltage and the load voltage. That load voltage sensing is because you want constant output voltage, and to maintain this constant output voltage, appropriate current should come from the source automatically, and that current is in phase with the voltage. No input current sensor is required. In the previous scheme, where we have used instantaneous current control using hysteresis current controller, we generated the reference current, source current, and then we compared it with the actual source current. So we basically require both voltage sensor, current sensor, as well as output voltage sensor. In this case, current sensors are not required, only the output voltage and the input voltage sensors are required. And as I said, that once the modulating signal is generated, you can compare it with the triangular one, and then at the intersection point the pulses are produced. The modulating voltage or the pole voltage will be same as plus Vd by 2 minus Vd by 2, and the phase voltage will be 2V by 3 or 1 by 1 V by 3 plus or minus. One thing which is well known is that higher is the carrier frequency, better will be the input current. Here you have the input currents for different values of the ratio, frequency ratio. P is the frequency ratio, carrier frequency to modulating frequency. You can notice that as the value of P increases, it is the carrier frequency to modulating frequency. Modulating frequency will be same as the supply frequency, because we are ensuring that the source current is same as the reference current. And we are generating the current for the rectifier. So the supply frequency is fixed, which is basically the frequency of the modulating signal. The only thing is carrier frequency we can keep on increasing. As the carrier frequency is increased, you can see that the current waveform has improved. Here it is becoming almost sinusoidal. Another thing you can notice that instead of taking an arbitrary value of this ratio, it is 9:15 like this. In fact, this ratio should be multiple of 3. Why multiple of 3? Because we want all the 3 phases to be identical. And if it is a multiple of 3, because carrier frequency is same for all the 3 phases, and therefore if it is multiple of 3, all the 3 phases will be modulated equally. Another thing is, it should be 3 times some factor. That factor should be an odd number, so that it is 3 times 3 9, 3 times 5 15, 3 times 7, 3 times 9, 3 times 13, 3 times 27. Why this? Because if it is an even number, then the positive half and the negative half of the output current, the source current, will not be same. We want both half of the currents to be same, so it must be an odd number. That is what. And here you have the frequency spectrum, which is shown for different values of this. Yes, frequency spectrum will be similar to your sinusoidal PWM modulation. There is one more scheme which is basically based on load commutated rectifier. Like this. Say in this sinusoidal PWM, we generated a sinusoidal current reference and then compare it with the source current, and the firing pulses are produced. So by doing that, we ensure that the source current is quite close to the reference current, and we have a particular harmonic spectrum. In the other one, where we have generated the modulating signal V mod by through computation, yes, we can achieve the desired performance. But in this particular case, it is, since we are controlling the current indirectly, so we cannot say a particular harmonic is absent or not. We can only say yes, the current is become much better and close to sine wave. If you want certain harmonics to be absent all throughout, we have to go for the selective harmonic elimination. But if it is a selective harmonic elimination, we cannot have that modulating signal concept to generate the pulses. What is required? Just recall the way we done it in that single phase converter, selective harmonic elimination method. We can use that method to find out what should be the position of the pulses so that certain harmonics are completely absent all throughout. And therefore the pattern is fixed, and if it is a fixed pattern, then and again that the position of the pulses cannot be obtained by comparing something. We have to put it in some processor or a memory, and that's why you have a digital control with fixed PWM pattern. And this synchronizing signal only ensures that this pattern is moved here and there. Now before coming to the control, let us see this particular phasor diagram. It is just like the previous one. You have V modulating signal plus RIS plus J omega LS IS. This is equal to V. You can also notice in this diagram that we are not even sensing the output voltage nor the source current. We are only sensing the load current. So if you want to keep the output voltage constant and you want controlled power flow in this, basically ID keeps on changing for different power flow, but voltage will be constant. For constant voltage VD, the modulating signal will be same. The only thing is, now the angle between V and modulating signal, that depends on how much current you want. So for different values of the load current, we can find out what should be the angle delta between V and V modulating. And in all the cases, the magnitude of V modulating will be fixed because DC voltage is to be kept fixed. So for fixed DC voltage, the magnitude of this is fixed, magnitude of this is fixed. Only thing is current is to be controlled, and for different values of current, we can find out what should be the angle delta. And that ID current versus delta we can plot. It is something of this nature. If this ID current is positive like this delta is basically a negative. Power flow is from here to here. You can also notice in this diagram, just like standard power system, if you neglect R, you have V and V mod, they are separated by an angle delta. So the power from the AC to DC side is, from AC to the load side, you can see, is the source voltage into modulating voltage divided by the reactance sine of delta. This is the power flow if you neglect this resistance R. And in this particular case, this V modulating signal lags Vs by an angle delta. So if the power is flowing from here to here, ID is positive. For positive ID, delta is negative. It may be a non-linear function. Similarly, if the power is going in this direction, ID value is negative, and therefore delta is become leading positive, and then the power flow is from this side to this side. So you have a non-linear function which you can store. And what will be the control? Sense the current, find out the angle delta, and this delta is basically, it is some offset you have to provide for the stability purpose, and then whatever is the value of delta, by that delta this PWM pattern is to be shifted here and there, and then the pulses are generated as per fixed pattern, which ensures that the modulating signal will be as per the diagram that will control the current IS through the node. Now the advantage of this particular scheme are, there is no input current sensor, no output voltage sensor required. That is the first advantage. It works on a fixed PWM pattern. Third is, it presents a very good stability, and in this case the stability of the system, it does not depend on the capacitor value. If you keep on working like this, the current can be made leading all throughout. You can have even zero voltage regulation, because this entire diagram is made assuming this voltage to be constant, and therefore this signal is fixed. Say if VD is fixed, then the pole voltage will be plus minus VD by 2, and if the pattern is fixed, then its fundamental component, it is also fixed. Problem comes, what is reported, that if this resistance is very small, then there is a stability issues, and that's why this method is not very popular in large systems. But otherwise it can be used, which reduces the current sensor here, which reduces the voltage sensor requirement here. Only one current sensor and one voltage sensor is enough, because rest of them can be shifted by 120 degree. This is all about improved quality converters. We started with the basic one, then we discussed how the input displacement factor can be made unity, and then by using these methods we can make the distortion factor also unity, thus the overall input power factor becomes unity. This is all about converter. From next class we will start with new chapter, maybe DC to DC converter.